Having just looked at the spring mass system with friction in it, it's important to be able to tie what we get in the mathematics to what we saw in the solutions. And we're going to introduce two new terms. Transient, which means passing with time, more specifically passing away with time, things that are not there in the long run, versus steady state, which is the long run behavior. We're going to return to the simulation for a second, and we're going to use these values here. So we'll use sine of 1, and we'll use 1 Newton as the magnitude of that, and our damping will be 1. And what we see is some jagged stuff at the beginning, and then it looks like it smooths out. Just to confirm that, hey, look at that. So we're pushing at a certain low frequency, and there is some damping. And what we see is this kind of jagged stuff at the beginning, and then eventually it settles into this long-term pattern. If we look at the mathematics, the solutions for the complementary solution, which have to do only with the left-hand side, are negative exponentials and cos of 5 and sine of 5t's. The non-homogeneous part of the solution gives us cos and sine of 1t. So how does that play out in this solution here? What are we seeing in the long run? Well, we have two natural frequencies in the solution. We have the e to the at cos of 5t and e to the at sine of 5t. Those are from our complementary solution. And we also had the simple sine of 1t and cos of 1t. Those were in our non-homogeneous part of the solution that came out of the forcing function. And if we ask ourselves which frequency is going to be present in the long run, well, that says t goes to infinity. Take a look at your two solutions. These exponentials are negative in the exponent, so these terms all go to 0. This complementary solution heads to 0 as time gets bigger and bigger and bigger. Meanwhile, this is present and has the same amplitude for all time. So that's nice because that lets us interpret the results back in the simulation. What we're seeing in the simulation result is jaggedy things. Let's work backwards. We have this curve oscillating. That's happening in the background with the non-homogeneous solution, but the initial conditions and things to do with the corresponding complementary solution are working themselves out in the first few seconds, but then fade away as time goes on because of that negative exponential. If we measured the frequency of this oscillation in the long run, it's going to be the frequency of the cos 1t, sine 1t, or 1 radian per second. And definitely not the oscillations due to this, because those have decayed away very quickly after the initial push. Can we generalize this? Well, if we have a damped physical system with forced oscillations, so our my double prime plus cy prime plus ky equals an F external, we are guaranteed that this yc is going to have e to the negative, turns out c over 2 t's in them. And that is always going to go to 0 as t goes to infinity because of that negative exponential. Yes, there's going to be some sines and cosines associated with that, but they're multiplied. They have an amplitude that it decays with a negative exponential. Meanwhile, the F external, if it's made up of some a sine bt, then our non-homogeneous solution is going to be some sine bt times a coefficient. We're running out of letters. Let's call that big C, plus d cos bt, and that oscillates forever. And so that is telling us, in terms of other terminology, that this will be the transient solution. It decays with time. After a certain number of seconds, you won't see the influence here, but this is going to dictate the steady state oscillations. And so what this means is if you push on some system at a given frequency, eventually it's just going to settle into a rhythm with that frequency. If you keep pushing on a spring at some number of radians per second, eventually the swing is just going to settle down and respond to that forever as you keep applying the force. whatever the working outs of the initial details, initial conditions, those are all going to fade with time. And so we get even more insight into not just how to construct these solutions, but what they actually mean in terms of the behavior of the system in both the short term and the long run. So just to recap, why do we spend so much time on this simple, it is a simple, spring mass system? Well, because it displays, maybe not all might be too much, but so many of the interesting mathematical solution forms. When we have the unforced, it has the complex roots, it has the real repeated, and it has the real distinct roots. And it has the pure imaginary, just roots of -1 solutions as well. So we get all the kinds of behavior that are possible for a second order homogeneous system. When we add the forced part to it, we get both the overlapping and the non-overlapping solutions. And we see what happens as we transition between those conditions and what that looks like. In particular, we saw that when they overlapped, there was resonance because we ended up with those non-homogeneous part of the solution looking like T cos of AT and T sine of BT, sine of AT. Whereas the non-overlapping could be a whole bunch of different behaviors, but it gradually led to beats, which was the thing that led to resonance if we snuck up on that exact overlap. So we hope with that, seeing all the mathematical analysis of that system, and ideally tying it back to your understanding of just a simple swing or a car going over a road with the shock absorbers playing the role of a spring mass system, this will give you some tangible idea of how these systems work and how they might tie into real-world behavior beyond the mathematics we've covered. Last but not least, as we saw, this differential equation for the spring mass system is either identical for the circuit with resistors, capacitors, and inductors, or certainly similar to a wide number of other real-world scenarios that lead to differential equations. So if you understand this system, you can often argue by analogy what you might see in other systems as well.